Hello, today we are still doing confidence intervals. The last two sections we've been doing confidence intervals for a population mean, but you can actually do a confidence interval for any statistic. So you could any population parameter. We can do it for you can do one for sigma, you could do one for the variance, you can do one also for a population proportion. So let's remember and review what that vocab is. These problems are binomial. So if you recall, binomial problems are situations that have only two answers, heads or tails, or yes or no, that kind of a thing. So typically in survey form, these are like yes or no questions. And when we encountered these in chapter 5, a lot of times the problems would start like this. 57% of Americans believe something, okay? Something that's a yes or no question, like believe that the president's doing a great job. Okay, so do you believe the president's doing a great job? Yes or no? That's a binomial situation. There's only two answers to that, as opposed to how much do you weigh? Lots of different answers. Okay, what I want you to focus on is this percentage here. Oftentimes binomial problems start with percentages, but not all the time. Another way that I could frame this problem is I could say, in a survey of 100 Americans, 57 of them said whatever we're talking about. Okay, now in order to create a population proportion, by the way, our letter for this is P, remember? Okay, that's our population proportion. What you do is it's a probability. It's the probability that if you chose somebody that they would answer yes. So it's the number of people who say yes. Now I put this in quotes, this yes, because P doesn't have to be the yes answers. It could be the no answers. It's just whichever one you're interested in. So that's usually like we label this our proof positive of whatever we're testing. Okay. Or you can make P always be the yes answer. It doesn't really matter as long as you keep it straight in your problem, what you decided was what. So typically whatever we're talking about in the problem, I just make that the P value, whether that's a yes or a no. So it's the number of people who say yes to your question over the sample. So basically in this second situation, I'm making it so that you have to build the percentage for me instead of just giving you the percentage, but it's still a binomial problem. So if you recall in chapter 5, I said, when I see a percentage, I think there's a very high chance this could be a binomial, but it doesn't mean it is. And just because there's a not a percentage doesn't mean there isn't. So you need to be a little bit careful with that. It's just a trend. Okay. And so it just kind of makes me go, I'm going to check if this is a binomial or not. Okay. So in this situation, I calculate P by going 57 over 100. And then divide that out and you get 0.57 or 57%, which is how that goes. Okay. Now, a little bit difference in notation. So typically in this book, when we look at P, we're going to be talking about the population proportion. This is the percentage of the population that says yes to our question. When we are looking at a sample, we use this P hat, okay? And so that's how we designate, that's kind of like the difference between saying mu or X bar. That's how those alternate. All right, so that's what we're looking at here. So the idea is the same. I want to know the percentage of people that believe the president's doing a good job. I can't actually survey the whole population. So I take a sample and I develop an interval around this population proportion. But now we're doing this all around decimals. So all my intervals are going to be decimals because we're doing percentages instead of means. And that's really the only big difference, okay? The formula is different, but the process is the same. So let's jump over to the calculator. Actually, let's look at a problem first. We're going to look at this first one, number 16. So in a survey of 2,303 US adults, 734 believe in UFOs. So my first step is to decide, is this a population mean or a population proportion problem? And I go, let's see, we're asking people if they believe in the UFOs. So if somebody said, do you believe in UFOs? I would answer yes or no. That means that it's binomial. And that means that I'm working with P and P hat instead of mu and X bar. So that's what designates this as a 6-3 problem, okay? And it wants to construct a 90% confidence interval for this population proportion. All right, so on class calc, we go under stats, we're going under tests, same place as all the others. And it's called this, a 1 prop Z interval. So it's a 1 proportion, it's a population proportion. And the population proportions are actually based off of a Z distribution instead of the T distributions. So we're going to click that and we're going to look at what they want us to enter. They want an X value. Okay, this is the X value is the number of people that said yes. The N value is the number of people you surveyed, and then the confidence level. So basically, they're going this calculator is going to use that X and N value to build your percentage. It's going to take that X and divide it by the N to get your percentage for your sample. Okay, so in this case, we're going to go X is 2303. Just kidding, that was the N value, huh? N is 2303, and my X value is going to be 734, say yes to UFOs. 734, and they're wanting us to build a 90% confidence interval. So this is going to be 0.9. And there's our confidence interval. Now notice the numbers are decimals. So that means that what I'm saying is, and listen to this language carefully, I'm not saying the mean, I'm saying the percentage of the population that, I'm talking about the percentage of the population that believes in UFOs. Okay, and my confidence in it interval is saying that's somewhere between 30% and 33%. Okay, so that gives me an idea of, hey, how are people at large going to believe in my population? Okay, again, same stuff down here. Here's your P hat value. This is your X divided by your N. So this is 0.32 for your sample, and this is your error right there. For my TI people, you are going to go to stat. You are going over to tests. And you are scrolling down past your T interval. Past 9, 10. This is my entry A. Okay, your calculator might be a little bit different, but it says 1 prop Z interval. Skip the 2 sample Z and the 2 sample T. We're not doing those. Okay, and it has the same entries. You have an X value, an N value, and a constant level, confidence level. So your X value is the number of people that say yes, your N is your total, and that's your confidence interval. Okay, great. Now, the other thing that we do in this section is we also are going to do minimum sample problems like we did in section 6.1. So let me tell you what the formula is for that. If you are interested in a minimum sample for a certain situation, sorry, my phone went dark and I had to pull up my photos again. P hat, Q hat, Z critical over E squared. So it's going to be a similar feel to what we did in 5.1. Let's run through that real quick. Here's a problem, 17. You wish to estimate with 95% confidence the population proportion who think that the president can do a lot about the price of gasoline. Your estimates must be accurate within 4% of the population proportion. So that statement about how accurate my estimate needs to be, this is my error, okay? And remember, error is always a decimal, okay? So, I mean, percentages, if it's a percent, it has to be a decimal. So this is going to be 0.04 down here. Z critical, we're going to calculate the same way we did in 5.1. I have got a normal distribution. Okay, these are Z scores, and I want a 95% confidence interval. That means that I've got 2.5% on each tail to total 100. And the question is, what's this Z score right there? So I'm going to go do my inverse norm if I'm on TI, or I'm going to do normal distribution dot CDF if I'm on class calc, and I'm entering the value 0.025. 0.025, my mean is 0, my standard deviation is 1. And sorry, I had something already on my calculator and I didn't show. There we go. This is going to be negative 1.96, and this is going to be 1.96. So again, you can use the negative or the positive value. It doesn't matter because we're going to end up squaring this. So I just use the positive 1.96. Now, P hat, Q hat. This is your sample proportion that say yes and your sample proportion that say no. There's two ways that this is going to work. If no preliminary estimate is available, okay, and we don't have any idea what percentage of the population thinks that the president can control gas prices, then we're going to use 0.5 and 0.5. The way the math works is that gives you, using 0.5, half and half, gives you the largest possible answer. So if you don't have a preliminary estimate, you just say, well, we'll take the biggest possible situation, which is when P and Q are 0.5, okay? So we crank this out. We're going to go 1.96. I'm going to divide it by 0.04. I'm going to square that. And then I'm going to multiply by 0.5 and 0.5, and I get 600.25. Now, remember, we're talking about how many people we need to sample. At minimum, I have to sample 600.25 people, which we're not going to cut somebody in a quarter. So I have to round up. This is 601. We always round up. If you round down, it's not a big enough sample. Okay, so that's how you do part A. Now, if there has been a sample pulled before now and we have some data, we can enter that for P or Q. So look at part B. Find the minimum sample size needed using a prior study that found that 48% of the adults think the president can do a lot about gas. So this is a previous study says, hey, we found out, this is part A, we found out that 0.48, that's a horrible color. Sorry, it doesn't show up very well. 0.48 of the population said, yes, the president can do a lot about gas prices. So if 0.48 is my P hat, then Q hat is going to be 1 minus 0.48, which is 0.52. All of this is the same. We're going to go 1.96, 0.04 squared, and let's crank that out again. 4 squared times 0.48 times 0.52. This is going to be 599.29. And we always have to round up. So this is going to be 600. So I know these aren't very different, but look at what's happening. When I don't have a preliminary estimate and I use 0.5, I get a bigger number than when I do have a preliminary, and I get 600. Now, why are they so close? Because 0.48 and 0.52 are not very far apart. They're pretty close to 0.5 and 0.5. But like, say you had a preliminary estimate of 0.27, and then your Q was off quite a bit from that, you'd find that your sample size would be significantly lower. So at the end of the day, what I want you to realize, just as a self-check, is if you don't have a preliminary estimate and you're using 0.5, you should get a higher number than when you use a study that's already been done. Okay, and that's what C is about. Compare the results. They just want you to notice that, hey, part A is bigger because you have to do a bigger sample if you don't have a previous study. So those are the two kinds of problems you're going to do in this section. Good luck. I will talk to you next time.